We have an active community on Slack, LinkedIn, Twitter, Instagram, and Facebook. Talking about our speaker today, Harshita is an applied scientist at Amazon. She uses machine learning to drive better decisions that influence AWS sales and marketing teams. She has deep expertise in building recommender system models, causal inference models for predicting downstream impact, and using various machine learning models to drive better business decisions. She's also an expert in deriving statistical inference from available data. She likes spending her leisure time in reading, cooking, and hiking. It's our pleasure to have you here today, Harshita. Thanks a lot for joining us today.
Thanks a lot, Gagana, for the introduction, and thank you all for joining. It's my pleasure to be hosting this session here. So I can start with sharing a presentation that I have created for everyone, which basically is about using recommender systems. My first introduction to recommender system was when I started working at Amazon. It was one of the first projects that I had to handle, and learning it then made me realize how often and how much it is used across all the industries, and how much we consume the contents from recommender systems in our day-to-day lives as well. So thank you everybody for joining. In today's session, I would be covering what recommender systems are, who is using them, why do we need recommender systems, a few examples of recommender systems, different types of recommender systems, their limitations, some of the metrics of how we can evaluate recommender systems, and also building a basic recommender system from scratch is something that we'll be looking at today. So let's start with what recommender systems are. So recommender systems basically are a subset of machine learning algorithms which are used to suggest relevant items to a user that would spike a user's interest. Now, somebody would think, why would we need recommender systems? So the content that a human can consume in a short period of time is very less as the content that is available on various websites, on various social media platforms, on various streaming platforms. There's such a huge variety of items to choose from that there comes to be known as an information overload problem for a user, where they do not know what should be the best item that they should be using next. Recommender system help us answer those choices. In return, if we are able to generate good recommendations for users, we end up getting better user engagement. We end up getting better sales and incrementing revenue, and potentially a better user experience for the users as well. So that's why building an efficient recommender system is something which each and every online platform has started doing from past, I would say, 5 to 10 years. And recommender systems have been around for much longer. The recommender systems that we will be discussing today, they were actually put in place by various companies like Amazon, Netflix, eBay back in somewhere around 2005 or 2006. So they have been here for a very long period of time. And there has been a lot of evolvement in recommender system that has happened since the onset of collection of vast majority of data. The next question that comes into picture is, who uses these recommender system? Any online platform that you can think of. Think of an e-commerce platform, a streaming service, social media platforms, your Instagram Reels, they use recommender system, TikTok, Facebook, your feed, any social media platform that you take into consideration. Your feed is curated from the recommendations that are specially personalized for you. advertising platforms use recommender systems to increase their revenues, basically. And then e-commerce platform, of course, have been using recommender systems since a very long time. Consider Amazon.com, eBay, all of these companies have been using recommender systems since somewhere around 1998. Amazon was initially using a recommender which was wherein humans were actually recommending products to the customers, which was started in 1998, and then they came on to ML-based recommender system, machine learning-based recommender system later in the days. Streaming services like Netflix, Amazon Prime, all of them use recommender systems. Netflix's collaborative filtering recommender system is very famous. You cannot talk about recommender systems if you do not talk about Netflix. Netflix is one of those companies which has done very in-depth research on what recommender systems are and how they have evolved along up to the point that they are now. Another company that I would like to mention in this would be Pinterest. Pinterest is also doing a lot of research on how you could improve recommender systems. Next question, I think this was covered already, like why do we need recommender system? We have such vast amount of information available, and then it exceeds the capacity of what users can consume in a day. And hence, to boost our engagement, maintain user interest, it's best that we give them all the relevant information that can capture as much as their attention. So we have like a 6 inches phone screen, and then the most number of relevant items that you can fit in that 6 inch of phone screen without the user having to scroll is kind of the best revenue and best increment in sales and the best user experience that you can give to a user. The next topic that we'll be discussing today would be types of recommender system. So today we'll be discussing 4 major types of recommender systems: content-based, collaborative filtering, hybrid recommender system, and graph recommender systems. Content-based recommender systems are the most commonly used type of recommender systems and have been around since, and are the oldest type of recommender systems that actually exist. They basically recommend items that are similar to current items. So what this recommender system works under the assumption that if you have, let's say, if you have watched a horror movie, then your next recommendation, then if you are currently watching a horror movie, then you would, and you're liking it, then it would recommend you more horror movies. Let's say someone has watched Iron Man, they liked it, then the recommender system would recommend to them more Marvel movies or more superhero movies. And similarly, if you like fantasy movies, if you have liked, let's say, if you have like Lord of the Rings, then it might recommend you to watch Harry Potter because both of them are based on fantasy worlds. So that's that is what content-based recommender systems do. Now, how do we build a content-based recommender system? To build a content-based recommender system, we need something which is known as a feature set of the products that we are trying to recommend or the items that we are trying to recommend. What I mean by feature set is, how do we describe these products? So let's say if you have a movie, then the feature set of the movie would be all the information about the movie, like what genre it is in, all the metadata, like who is the director, what is the running time, who are the actors in the movie. Now, when was this movie released? How was it taken by the audience? And all such information about what was the plot of the movie, and all such metadata information or attributes about the items or the products are used to create the recommender system. So to implement a content-based recommender system, we first represent all the metadata or all the information that we have about our products or our items as a vector. And then once we have done that, we can calculate a pairwise cosine similarity. So let's say you have 10,000 movies in your data set. and you have something known as the plot of the movie, you have the director of the movie, and you have genre of the movie. You can represent all of this as a vector. And then you can create a 10,000 cross 10,000 matrix, and each of each of the values in this matrix would be like, let's say movie A and movie B. What is the similarity score, cosine similarity score of movie A with movie B, and then like movie A with movie C, and then 10,000 and such values. What we then do is we check we take the movies which have the most similarity score with the movie that we have in question or the item that we have in question, and we recommend those items or those movies as the next best for a customer to watch. Now, let's think about this. It's possible that if you think about an e-commerce platform, let's say eBay, for example, eBay has like billions of users and millions of products. So now if you try to implement, n cross n matrix here, then it would be very time consuming to calculate a similarity measure for all the items with all the other items. So how do we combat that problem there? Well, we do something known as clustering. So first, we suppose if there's a new item that comes on eBay, it would be clustered into a hierarchy. Something like, is this an electronic item, or is this a home and furniture item, or is this a clothing item? Something like that. And then once you have a new item that is coming into picture, or if you want to recommend an item which is similar to this particular item, you only look at all the products which are in the same hierarchy or are in the same cluster, and then you only recommend and only calculate the cosine similarity for those items in that particular hierarchy. Like if you have a cell phone, then you only calculate the similarity of the items with all the available cell phones or with all the available electronic devices, and then you recommend the next best item for the user. Now, there are a few drawbacks of content-based recommender system. Obviously, that's why we have other types of recommender systems. The first drawback is scalability. So as I said, a website like eBay will have so many sellers who are onboarding that website each and every day, and there are so many new products that are being onboarded. So every time a new product is onboarded, what they have to do is they have to add the metadata of that product into the recommender system, and then run the model and generate the cosine similarities all over again, which becomes very time consuming, and this is something which is not scalable. The other problem that arises with this is, let's say you are somebody who has just bought or who has been browsing a cell phone. Now you bought a cell phone, and if you're only using content-based recommender system, according to the similarity measures, most of the products that will be next recommended to you are cell phones. But now you already have a cell phone. You don't need those recommendations. What you are lacking here is diversity of products. So content-based recommender systems fail to provide diversity of products for users, and hence they are not always useful after the purchase has been made. If you take the scenario of a book or a movie, then you have read a mystery novel, you liked it. You read another mystery novel, you liked it. But it's not important that you'll keep reading that novel you'll keep only reading mystery novels. You might want to go to some other genre as well. So those are a few drawbacks of content-based recommender systems. To combat those, we have another type of recommender system, which is known as collaborative filtering. So collaborative filtering works under the assumption that past similar user preferences can help us predict upcoming preferences. So let's say we build an ML algorithm that predicts what items might interest a user based on the past preferences of similar users. So what we do is, if you think about a website, you have browsed something, you always get recommendations like users who are similar to you were also interested in something like this. So those type of recommendations are usually coming from collaborative filtering recommendations. Like if you're on a clothing website and you get a recommendation like users who were similar to you or users who bought this were also bought this, those type of recommendations are usually collaborative filtering based recommendations. So collaborative filtering can also be divided into two parts. Those are like memory based recommenders, and the next one would be model based recommenders. So in memory based recommenders, we have again two types of recommenders: user based and item based. So let's talk about user based recommenders. What happens there is you take a user, you look at which are the users which are most similar to this users. So let's say you have 1,000 users and you have 10,000 products. Now, these set of 1,000 users have used subset of these 10,000 products. You take user A. User A has used, let's say, 10 products. You look at all the users who are similar to user A. So let's say you have user B, C, D, and user B, C, D have used 8, 7, 9 types of, 9 type of products that user A has used. So we are working under the assumption that the products which were also liked by user B, C, D, and E would be liked by user A because they are kind of similar in their usage patterns. So how do we start is we create a neighborhood. Like we take a user, we create their neighborhood. Like that means we calculate similarity scores of this particular user with all the other users who are present in our neighborhood. And once we have these similarity scores, we then look at the other items that this user is using. So what we then do is, let's say we want to rank an item I. The user U needs to rank an item I. What we do is, we say that U and V have a similarity score of 0.5. V has weighted this item as somewhat around, out of 4 stars, it has rated this item, out of 5 stars, it has rated this item as 4 stars. We multiply the similarity of users U and V with the rating of what user V has given. And then we sum this up and then we divide it by all the similarity scores that we have for all the users in that neighborhood. So basically what we are trying to do is we are trying to calculate how much would a user rate an item given the ratings from all the other users who are similar to this user. The other type of recommendation that also comes here is item-based ranking. So here we basically start with a user, and in user-based we start with a user and we create a neighborhood of similar users. In item-based, it's reversed. We start with the item and we look at all the other items that are similar to this particular item. Now you would ask, what would be the difference between the content-based filtering and the item-based filtering and the item-based collaborative filtering? So for content-based recommender systems, you need something which is known as a feature set or an attribute. For item-based, you are not looking at any of the features of these items. You're only calculating the similarity scores based on which users have used this item. So you can think about this as something like you have a matrix which has all the users, 1,000 cross 10,000 matrix, which has, let's say, 1,000 rows for all the users and 10,000 columns for all the products. So let's say every item can be represented as 0 or 1 value, as 1,000 dimension 0 or 1 value based on if a user I has used it or not. So we again create a neighborhood for these items. We look at which are the users, which are the type of users which use these items, which are the other users, like what are the other items that these users are using, and then we recommend those items along with this item. So if you want an example about this, then let's think about Amazon. If you are browsing something on Amazon.com and you search for a product, if you go down, you will find items similar to this particular item. Those or those are the type of or the items which are also brought together with this item. So let's say if you are searching for dumbbells and you see a vibrating plate being recommended, or stretch bands being recommended, or any other gym equipment being recommended, then those are based out of item-based collaborative filtering. That means you try to see if a user is using an item A, then what are the other items that the same users are using? The other type of implementation of collaborative filtering comes from model-based recommendations, which is also known as matrix factorization. So what you do here is, let's say, again, you have represented this particular user and item interaction matrix, and then at some places you do have a rating, on the other places you do not have a rating. So how do we find, let's say you have 1,000 movies, here, and you have 100 users here. Not all 100 users have viewed all of these 1,000 movies, right? And we want to have one matrix which has ratings for all the 1,000 movies by all the 100 users. How do we get that? So matrix factorization is something that helps us get there. How do we get it? Is we create something known as latent factors to predict the ranking for all the items in a utility matrix. What a utility matrix is? Utility matrix is nothing but a user item interaction matrix. So what we are trying to create here is, we create, so let's take a step back. The idea behind matrix factorization actually comes from something known as singular value decomposition. So singular value decomposition basically says that you can represent every matrix as a multiplication of 3 matrices. And then one of those matrices is the eigenvalue matrix, and then the other 2 matrices are the left singular matrix and the right singular matrix. So we try to use the same principle here. We are trying to generate this user item matrix from by creating a user cross k dimension matrix and a item cross k dimension matrix. So basically, we try to represent every user in k dimension, and similarly, we also try to represent every item in k dimensions. Now, what are these k dimensions, or what are these k latents is unknown to us. That is something that the model needs to learn. So what we are trying to do here is, so let's say if I multiply this with this, if I do this matrix multiplication, then whatever number I have here, it should be closest, the multiplication that I get from here should be closest to the number that I'm getting, is the optimal goal of matrix factorization. How do we get that? We try to represent the rank matrix as I said, 2 matrices of latent factors. And then we try to minimize the error rate. So basically the multiplication of this, the dot product of this with this, whatever value we have here. So whatever comes out of this resultant matrix, whatever the value is obtained here, we want that the error rate there is minimal. So let's say if the rating here is 5, we would want the rating that comes after multiplying these 2 matrices as close as possible to 5. So now someone would ask, how do we get that? How do we minimize for this? So to minimize for that, what we do something which is known as gradient descent, something that every ML algorithm does. We start by randomly initializing these 2 matrices, and then we use the gradient descent algorithm to minimize this function right here. This function is nothing but the multiplication that we get out of here, and for the ratings, where we have the ratings present, the difference between the original rating minus the predicted ratings where we have present should be as minimal as possible. So that's what the gradient descent is trying to optimize for. And after iteratively doing that, we reach to something, we reach the minima, and then we can finally have, we'll finally have one matrix which will have all of these values populated. And then we can suggest the products or the items which are not currently being used by the user but have highest user ratings as the next best items for the particular user. So that's for matrix factorization based collaborative filtering. Now,
I'm sorry to interrupt you, Harshita, but before we move forward, one of our participants wanted to ask if you could enlarge the screen.
Oh yeah, sure. I'm sorry. So
Thank you.
Give me 1 second. Then is this good?
That looks great. Yes.
Sounds good. Thank you. The next and third type of recommender system that we'll be talking about is hybrid recommender system. So before that, what are some of the problems that this collaborative filtering recommender system has? It has something which is known. There is one problem which is known as the cold start problem. So the cold start problem basically means that if there is a new user, then they have not rated any of the items. So you would not know anything about this particular user. Or let's say if there is a new item, then there is no user who would have rated that item. How do we recommend, recommendations regarding those items or for those new users? To bridge, that's one of the problems of collaborative filtering. And that also brings us to something which is known as matrix sparsity. So if you think about the collection of movies that or the collection of products that eBay has and the collection of movies that Netflix has versus the number of users. So it's the matrix of user and item or the user and movie interaction would be something which is very sparse. So let's say in our lifetime, maybe I would have watched 1,000 movies, and then Netflix might have somewhere around 100K or 200K, or let's say 500,000 movies. Then if you think about me as a user, then for me, out of all of those, 500 columns that represent movies, only 1,000 would have values because that is how much I would have watched and that's how much I would have rated, right? So that if you now most of the value, because most of these values are null and we only have very limited values, both doing model-based approaches or matrix factorization becomes very difficult when it comes to collaborative filtering of large models. So how do we, approach that problem? There's a third set of recommender system that might help us approach this problem. And that third set of recommender system is known as hybrid recommenders. So what hybrid recommendation does is it basically combines recommendations from both content-based recommendations and collaborative filtering-based recommendations. So think about any new platform that you join. You are always, think about Twitter. Whenever you join Twitter, it usually asks you what are your preferences that you're interested in initially before, recommending you anything, because Twitter doesn't have any information about you. They do not know what to recommend to you. So if you select, like, let's say you're interested in politics, you're interested, let's say you're interested in movies or Bollywood, Hollywood. If you're in, let's say you just say that you're interested in environmental sciences. So what we could first do is we first use content-based recommender system to recommend relevant feeds for you. So if you have selected politics, then all the tweets which have which are most related to politics or which have the highest number of shares when it comes to politics, or highest number of interaction when it comes to politics, has the highest number of hashtags that relate to politics, would be displayed on your feed. And similarly, all the other interest areas that you have selected, all of those things would be populated on their feed. And now likewise, according to your interaction with the feed, once Twitter has enough data about you, they can, I'm not saying Twitter uses collaborative filtering, but any platform could then use collaborative filtering to recommend the next best, item for you to interact with. So that's how hybrid recommendations would work. Another way to use hybrid recommendations would be a weighted approach. So let's say we are, whenever you look at any like if you go visit your eBay homepage, or if you go visit your Amazon homepage, it will tell you what are the next items that you should buy, and also what are the items similar to the items that you have already bought. So let's say if you have already browsed. So let's say you were browsing for cell phones. So eBay would show you similar items that you have browsed, so recommendations for cell phones, and then rest of the page would have recommendations for items which are similar to cell phones, and then to your prior searches as well, like whatever you would have searched prior to that, that would be appended there as well. So basically using a weighted approach, like I want 20% of my recommendation to come from, similar content, and I want the rest of the 80% to come from collaborative filtering. You could use that approach again to generate recommendations. Then there's something else which is known as cascading. Basically, you first filter out items using collaborative filtering, and then use content-based recommenders to recommend better items, or vice versa, like topping one type of recommender over other to generate better recommendations. The final type of recommender system that we'll be discussing today is graph-based recommender systems. These are pretty new, and there's not a lot of research that is around these recommender systems as of now, but they are something which are the hottest topic of research in recommender systems as of now. So if you get a chance to try your hands on graph-based recommender systems, it would be amazing. The idea is very basic. It says that you can represent the interactions between users and items as a bipartite graph. So let's say you have users, you have movies. You create a bipartite graph. If user A has watched movie, let's say 1, 2, 3, then you create an edge between user A and movies 1, 2, 3. And the weights of these edges would be the ratings that you would have given to these movies, basically. Now, once you have done that, it becomes a link prediction task with weights of what weight would, suppose a user 1 hasn't seen movie, 3, 4, and 5. According to the link prediction task, would there be a edge or a link between movie 3 and user A that would exist? And if there would be one which exists, what would be the rating that user A would give to this particular movie? How we do that is, how graphs do that is, there are two approaches as of now. One is GNNs, which are based over graph stage, and the other approach is random walk. So what GNN does is, GNN says that I'll create embeddings of all of the nodes. So all the information I have about the users, like let's say all the demographic information, all the preference-based information, everything that I have about the user, I'll represent it as one embedding. I'll do the same with all the information that I have about the items or the products or the movies. I'll represent them as embeddings as well. And then I have one other matrix, which basically would have information about the interaction between users, which would have learned about interactions between users and items. So here in this equation, UI basically means that what are the embeddings for user U, like a matrix of embeddings for user U, a matrix of embeddings for user for items V, and then this is an interaction matrix between you and I. And then we do a soft max over it to find what is the probability of what would be the probability of having a link here. So let's say we are trying to predict if this particular user would like this item or this particular user would watch this movie. We do a ring, we calculate the probability of having a link here, and let's say of having a rank 4 here. So P of this link of this value being 4, what is the probability of that? And then whichever rank gets the highest probability, that would be the weighted average that we give to this particular edge. The next, so that's how GNN works, like graph neural networks work. The next type of, another simpler way of learning from graphs is generating recommendations from graph is something which is known as graph random walk. So you basically start with this particular user. You look at all the items that this particular user has interacted with. So let's say user A has given 5 star to this item. I go to this item. I see, okay, which is the other user that has used the same item? Oh, this user has used the same item and has given, let's say, 5-star rating to that item. Amazing. Then what I see is, what is the other item that this user has used? Now, because both of them are using these items, that means they belong to a similar or a closer neighborhood. They are very similar to each other. So the item that is being used by this user, or the rating that has been given by highest rate. So suppose this item has been given 5-star rating by this user, then it's likely that user A would also give 5-star rating to this item. So we do such numerous numbers of walk, and then we count how many number of times do we land on each product and what is the average rating that we get for that link. And whichever products we land on the highest number of times, those are the products that we assume or we quantify that the user would end up using. So that's the third type of recommender system, which is graph-based recommender systems. The next topic is, how do we analyze how effective is our recommender system? There are many ways of doing that. So one is precision at K or recall at K, which basically means if you're recommending 10 products, how many of those products were actually used by the customer, divided by the true positives plus the true positives plus the false positives, or the true positives plus the true negatives, according to the definitions of precision and recall. And then those can be used as metric in deciding which recommender system works best for you. The third metric is hit rate. So let's say if you have this particular screen and you have 10 items recommended to a user, how many of those items did the user click on or interact with could be one of the metric that is used. The third and fourth type of matrix are normalized discounted cumulative gain and mean reciprocal rank. So to start with mean reciprocal rank says which is the first relevant item that you recommended to a user. So let's say the user was searching for cell phones, or let's say the user was searching for Adidas shoes. And the first item that you recommended to them was a Samsung cell phone. The second item that you had recommended to them was an Adidas shoes. So the first relevant item was on rank 2 here for your user. So that is something. So it would be something like the inverse of that rank. So 1 by 2. So your mean reciprocal rank there will be 0.5. So in an ideal scenario, if your recommender system is working best, your mean reciprocal rank should come out to be 1. As less the mean reciprocal rank, the better your recommender system is, because that means that your relevant recommendations are coming much earlier than what are coming much earlier, and hence the user doesn't have to scroll enough. Next type of recommender that we have is, the next type of metric that we have is normalized discounted cumulative gain. So to give a brief overview, what we do in normalized discounted cumulative gain is, we create a scale of 0 to 3. 3 represents that the item is most relevant. 1 and 2 represent the item is somewhat relevant. And 0 represents that the item is least relevant. And what we do then is, we first calculate which were the items which should have come first, which were the, and which, so what we do is, let's say our first item is okayish relevant, our second item is, somewhat relevant. We give these scores to all the items and then we divide them by the log of their place. So, and we add them over. So let's say the first item that you have, it had the relative score of 2 and its position is 1. So it would be like 2 divided by log of position 1 plus 1 plus the, let's say for the second item, your relative value was 1. So there the value would be 1 divided by log of the position of the item, that's 2 plus 3. We do that for all the items. And then we see what would have happened in an ideal. So we call this as DCG, which is known as discounted cumulative gain. And then we divide it by ideal discounted cumulative gain. What is ideal is the one which has value 3, the one recommendation which is the most relevant should be coming on, the first on your screen. So what we do is we calculate the same, DCG for how the ideal scenario should look like, and then we divide the DCG by the ideal DCG to get something which is known as normalized cumulative gain. So we do this to penalize, like let's say if there is a recommendation which is really relevant, but it's coming, later, then you're giving a penalty to the system or to the model that this is not good, like the metric that we are calculating is not good, versus if there's a recommendation where the most relevant is coming, let's say if second instead of fourth or fifth, then we are saying, okay, this recommender system makes more sense than the others that we have. So I think that's it for the slides. The next part is I've created a very short Python notebook with a demo of creating a very simple content-based recommender system. You can find it in the chat. I can open it here. So basically the data that I have taken here is from Kaggle. It's a Goodreads book data. What we are trying to do in this file is we have something which is known as book names, we have book IDs, we have book ISBNs, we have authors. Along with that, we have book tags, and then we have tag IDs. We merge all of this and we create a data frame. Then what we do is we try to create a context for this book or a corpus for this book by combining the tags of this book plus the author of this book plus the title of this book. The next what we do is we try to vectorize this corpus. Now it becomes an NLP problem. Oh, okay. I think my screen sharing has been paused. Sorry. Let me try and share again. Okay, give me 1 second. Okay, I think now I'm sharing the screen. Yeah. So as I was saying, we have this book data frame, which has book tags, which has book IDs, and which also has author names and stuff. We try to create a corpus by combining this. Then we try to vectorize all the information that we have. That means we try to we use a TF-IDF vectorizer to generate a vector representation of all the text we have. And we use cosine similarity here to calculate the similarity of all the books with all the other books. So let's say we had, somewhere around maybe, okay, I think I'll have to run it all again. But yeah, basically what would happen here is, so we have this books data frame, we create a similarity score, we'll ask it what are the books which are similar to, the First World War book, then it'll give you 5 books which are the most similar to this book, and then if I ask it to give me the next, best recommendation for this, then it'll also, for the Great Gatsby, it will give me 5 books which are the most relevant to the Great Gatsby. It's a very simple content-based recommender. This again becomes an NLP problem of how you want to, define your vectors. You could use word2vec. You could use any other embeddings to find similar vectors, or to create vectors out of the corpus that you have, and then try to generate similarity. Again, you can use any similarity measures. Cosine is something which is the most used across the industry, and is the most used for document similarity, but it again depends on the context of your problem. If you want to try and test with other similarity measures, you're very open to do that. So that's it for today's presentation. Does anybody else has any questions? Let me stop sharing my screen. I guess we don't have any questions. Oh, okay, so I think, do ad blockers affect recommended systems? So the answer to that would be no, because so it happens when you're there should be a feedback mechanism between the ad blockers and the ads that you're seeing. So the ads that you're seeing, maybe, they're coming out of Google ads, let's say, then I don't think there's a feedback mechanism in place where the ads that you are which tells Google ads that you have blocked an ad. But if you click on the, cross button over the ad, then maybe Google ad would get a feedback that the user is not interested in this ad and might not recommend to you. When ad blockers do not go as a direct feedback to Google ads or to any ad displaying website, as far as I know.
Harshita, I guess we have another question. One of our attendees want to know if one of the filtering techniques can be better than the other.
So for collaborative filtering, I think it kind of depends upon what type of data you have. It's sometimes possible, let's say if you're using, memory-based collaborative filtering techniques. So if you are using something like, let's say, k-nearest neighbors to first create your neighborhood and then, generate recommendations based on those neighborhoods, then if your data is not good enough to give you, a good scenario of what similar users or similar neighbors would look like, then at that point in time, matrix factorization works better over, model based. And it also depends upon the amount of computational power you have. Matrix factorization takes more computational power as compared to memory-based approaches. And then it's a bit difficult to implement as well.
There is another question. Are visitors who drop off and don't purchase a factor as well in the recommender system, or it is only for people who complete purchases?
No, if it again depends on which company's recommender system you are referring to, but mostly if you are browsing an item, even if you haven't purchased it, it would give you options about, do you want to continue browsing this, or do you want to items similar to the items you have browsed before. So it is not only about what you have purchased, it's about the level of interaction that has been stored. So if the company if the website that you're interacting with stores this interaction that you have clicked on an item, then they would use it to generate recommendations for you. And then I think, okay, in the Q&A, there's one more question. Do you recommend other resources to learn about recommendation systems? Yes, there are many resources that you could use. There's a book known as Recommender Systems. You could start with that. Or there are many GitHub or Kaggle notebooks that I can, point you to, which could be helpful in implementing matrix factorization or graph-based recommender systems. It depends on what type of recommender systems you are interested in. If you're interested in graph-based recommender system, then the field is a bit newer as compared to, and it's a bit more recent as compared to the other recommender systems, and are still being onboarded by many industries and many companies. So I would say getting more resources on graph recommender systems could be a bit difficult as compared to resources on hybrid collaborative filtering or content-based recommender systems. But you could start with, there's this book, Recommender Systems. It would give you an overview. And if you want to know about graph recommender system, then I would say research papers would be a good start. Aside from clustering algorithms, are there any other type of algorithms that are popularly used in industry? Yes, definitely. So the matrix factorization algorithm, which uses gradient descent, it actually a few tweaks to that algorithm, and it won $1 million prize in somewhere around 2009 or 2008 by a contest which was hosted by Netflix. So Netflix hosted a contest to improve the recommender system, and then matrix factorization based technique, and 100. So the winning team, they kind of combined results from 100 recommender systems to come up with a better recommender system. So definitely, and then there are in industry, the recommendation techniques that are used are much more complex as to the ones that we have discussed here today. These are more simpler. You add much more context to the data, and you add much more context to the data, or you add much more context about a person or a user, and then you generate a recommendation using one of these methodologies. So if you want to know the exact, if you want to know the exact algorithms except clustering that are used, then I would say gradient descent for matrix factorization, random walks on graph is also used a lot. The third algorithm that's also used a lot is graph neural networks, which is being onboarded a lot, actually. It's not being used a lot, it's being onboarded a lot by many companies. And then the other algorithm is for item collaborative filtering, which initially started with clustering, but it now does, which is something known as, it first creates an embedding and then clusters it. It does clustering in the end, but first it uses neural networks to create embeddings and then clusters. And that's also being used in a few of the companies. So is this data science role housed in product marketing or ads team? So recommender system actually can be used by any of the teams. So it can be used in the social media feed team. It can be used in the products team, marketing team. Recommender systems are, I think, present everywhere. And I think as far as my understanding goes, if you are in an industry doing a data science job, then you can be asked to do you're expected to know various things. It's not only specific type of teams would ask you to build recommender systems. I believe recommender systems are usually present everywhere. But even in internal Amazon tools, I could give you a very basic example of recommender system is like when you're trying to optimize your search queries. So when you're doing a search and you're trying to optimize it, and the first search results, Google's page rank algorithm is also a type of recommended algorithm. So yeah, I think there's no, I don't think it's housed in any one particular team. I think it's for most of the teams that are present, or most of the products that are present. All of them could have different type of recommendations, but like what type of recommendation? So let's say you're a sales team, then you might use recommendation for lead generation. So if you're a marketing team, or sales and marketing team, then sales team would say, okay, what do I sell to this customer? Marketing team would be like, what customers do I reach out to? Ads team would be like, which ads do I display? Product team would be like, where on the search engine should my product come? But I think this is based in all the in most teams, and it's not particularly defined to one team. Next question is, do you think that these recommenders are as they are being used by e-commerce companies are automating shopping instead of leaving things to a chance? Yes, of course. And I think that is I wouldn't say leaving things to a chance, because most of machine learning revolves around probability. Any machine learning algorithm that you're using um, has the uncertainty assigned to it. So let's say we are trying to see that this is the most probable product that the customer could be interested in. And that's the whole point of it, is to increase user engagement. Because if you see a product, let's say you're buying a cell phone and you see a cell phone cover along with it, then you think, oh yeah, I'm buying a new cell phone, then a cover along with it makes sense. I should probably buy it together. So e-commerce platform is increasing its sales, increasing is increasing user engagement, and is kind of also increasing customer satisfaction, because you do not have to think about you do not have to think about what else should I buy along with it. I think it's already served on the plate there for you. So it kind of even simplifies things for you a bit. Recommenders, they are sustainable, but then there's a lot of evolving that has been happening around them. So let's think about the oldest recommender system, that is, let's say, think about the content-based recommender system. There are many, because they increase consumption. I mean, buying and not buying is something which is okay. So you're trying to ask me, do you think recommender systems are sustainable technology because they increase consumption? They do not increase unnecessary consumption, in my opinion. If you're buying a new phone, you might, however, end up buying a phone cover as well, right? So it's just a matter of, would you be buying it after 2 days, or would you be buying it right now? It's just a matter of time. So that's why I think they are kind of sustainable, because they don't promote you or provoke you to buy things you don't need. They only suggest you things that the other users are using. If you find that those things are something that would be useful to you, you go ahead and buy them. If you think those are the things that are not useful to you, you just don't buy them. So graph neural networks definitely add more complexity to the recommender systems. However, graph neural networks also help us in adding more context to the recommender system. So if you think about collaborative filtering and content-based recommender systems, then up to this point, if let's say if one of them is using information about the items, then it's not using information about user item interaction. The other one is using information about the user item interaction, but it's not using information about the about the item features. So graph neural network help when you have a lot of knowledge about the when you have a lot of knowledge additional about the users and the products and about the whole domain and the context. How do you add that knowledge? You add that knowledge, you represent that knowledge using embeddings, and graph neural networks help you get those embeddings and hence generate recommendations. So they do complex it a bit, but then they also help you add more context to the recommendations and improve those. I think we have no more questions.
Yes. And that was a very insightful and in-depth talk on recommender systems. I personally found the explanation for graph-based recommender system very interesting and hope to work on it. So my question for you is, for a beginner who is starting out with recommender systems, would you recommend starting off with graph recommender systems?
No, actually, I would rather recommend starting out with collaborative filtering, and like content based recommender systems is basically just cosine similarity, so that's fine. But I would personally recommend you going on maybe Kaggle and working on one or two ways of implementing a collaborative filtering recommender system, and then working with graph based approach, because it's not important that every time a graph based recommender system would work well. If your data is smaller, then collaborative filtering could give you best results, but if your data is really large, then only neural networks can make sense. Like, it's the basic idea behind neural networks. If your data is bigger, only then neural networks can generate insights from it. On small data sets, neural networks doesn't work well. So I would first recommend starting with collaborative filtering, because usually what happens is until we are working with very large data, we are not required to work with graph-based recommender systems at all.
Thanks a lot, Harshita. It was a pleasure having you on board.
Thank you so much for having me, Gagna. Thank you so much, Mihir. If you have any other questions, let me know. I would be glad to answer it. It was a pleasure joining. Thank you all.
Thank you, Harshita. Thank you, Gagana.